So the purpose of this lab is we want to watch an energy conversion in process. Okay, like we want to watch it in action. We want to see it happen. Okay, and we want to take some measurements that will tell us how efficient or how much of the initial energy becomes energy at the end. Okay, does EI actually equal EF? That's stuff we've been working on over the past few days. Spoiler alert, it doesn't. Okay, at least not mechanically. Will there still be the same amount of energy in the system? There will. It's just going to be, what's going to happen to it?
Will be released as sound or heat or friction or something else?
Yeah, friction will actually cause it to be turned into other forms of energy. Okay, heat, sound, okay, stuff like that. So that's what we're looking at here. Okay, so to help you with the design of this, we are comparing the initial potential energy of the cart to the final potential energy of the cart. That's it. That's all we're doing. Okay, we're going to run a few trials just to get some data to average. Okay, but in the end, the purpose of this lab is to measure how much potential energy there is initially. Where does that come from? Like, we're going to put this cart on the top of this ramp, and then we're just going to let it go. Okay? Where does it get its initial energy from? Okay, it's going to be gravitational potential energy. Where does it get that energy from?
From its height.
Okay, its height is part of what, how does it get there? Work, exactly. It gets there, it gets that energy because we as the experimenter are putting it there. Okay, there is no experiment to be had unless the experimenter does some work, okay, to put the cart at the top of the ramp. Otherwise, there's no potential energy to turn into kinetic energy later. Okay, so the thing we're measuring, okay, or wanting to compare, we're not actually measuring it, okay, is that we are going to be looking at the kinetic energy at the bottom of the ramp. Here's the problem with that. There is no way to directly measure the kinetic energy at the bottom of the ramp because we would need to know how fast the cart is going at the bottom of the ramp, and we don't have a way to measure that. So, what we're going to measure instead is how far the car travels past the end of the ramp on a level surface until it stops. Okay? So, to reduce confusion, the main responding variable here is the final kinetic energy. But because we can't measure that directly, we're going to be measuring a few other things that you don't need to list as responding variables, okay? Because I don't want you to get confused here. Okay? Once the cart leaves the ramp and is now traveling on the floor, what brings it to a stop? Friction. Okay? Friction is going to bring it to a stop. Since we're going to, run this experiment, same ramp, same piece of floor, same cart every time, okay, all that kind of stuff needs to stay the same for a few reasons, reasons. Okay? We should be able to figure out how much energy the cart had at the bottom of the ramp based on how far it travels before it stops. Okay? And the reason we're going to be able to do that is because of what you guys just told me. Friction is the force that's going to stop the cart. We're going to measure the distance over which that force acts. And we're going to time how long it takes the cart to stop. That way, we can get the force of friction, we can measure the distance. What will that calculate? What's force times distance calculate? Work. Will the work done in stopping the cart be equal to the kinetic energy it had at the bottom of the ramp? It should be. I mean, the only reason the cart comes to a stop is because friction does work in order to take away all of its energy. Okay? So what we're going to do is measure a couple of things that will allow us to indirectly get the energy at the bottom of the ramp. Okay, so let's talk about the hypothesis and then we'll talk about the procedure. So in the hypothesis, if, and then statement, as we always do, okay, the if part basically needs to tell me what does the law of conservation of energy say? Put the law of conservation of energy kind of in your own words. If the law of conservation of energy says blah, blah, blah. Okay. The and part is always going to describe the experiment. A cart's going to be placed at the top of a ramp and released. And it's, you know, the distance it travels will be recorded or something like that. That's generally what we're doing. Then, predict your results. Okay? Will your kinetic energy at the bottom be equal to the energy at the top or not? And explain why. So it'd be, then the energy at the bottom will be equal because, or then the energy at the bottom will not be equal because. Okay? That's what I'm looking for in the then part. Okay, a few things that we're going to have to measure, okay, during this experiment. Hopefully I have one working scale. Yeah, okay. That was working. Okay, so there's some things we're going to have to measure. First off, we need to know the mass of the carts, okay? There's two different kinds of carts, so that'll be important. Okay, if you get a black cart, okay, black plastic cart, this is also important. Black plastic carts go with wooden ramps, okay, and they get oriented this way. Notice how the ground clearance is different this way than it is this way. The cart is not a low rider, okay. If you put it on the ramp like this, it won't go anywhere. So it needs to be put on the ramp like this. You'll know if you do it wrong because it won't roll, okay. So it needs to go on the ramp in this orientation. And the black carts are all the same and have a mass of 0.468 kilograms. Okay. There are also silver carts. Silver carts go with silver ramps. I try to keep it simple. Okay. Silver carts are 500 grams. So 0.500 kilograms. Okay, so that's the number you need. Now you guys don't have to measure them because carts are all the same. Okay. All right. Other things we need. We need the initial height of the ramp. Okay. Notice how tall the one in the picture is. Don't make this higher than 15 centimeters, or, because we need it in meters, 0.15 meters. If you make it any higher than that, the cart goes too far and starts running into stuff, okay? Because we need it to stop. And if we make the ramp too high, it'll just go too far, okay? So the ramp maximum 0.15 meters, okay? Everybody with me on that? So you have to measure yours, whatever it ends up being, okay? And keep that same height. For the kinetic energy, obviously we need the mass of the cart, which we already have. We need the distance traveled by the cart after it leaves the ramp, okay? And the time of travel. So the person who's timing needs to be on the ball because you're only timing the cart once it's on the floor. So you've got to watch it go down the ramp, start the timer on your phone as soon as the wheels come off the ramp. And stop the timer as soon as the cart stops. Okay, now the cart's going to slow down, so you got to really be watching it. Be sure it's stopped when you stop the timer. Okay, everybody with me there? Easy question.
Is it when like
front wheels hit, or like do all the wheels hit?
It happens pretty fast. So I would say aim for the front wheels, and if you do that with your reaction time, it'll probably be when the whole cart is on the ground. Okay? All right. So those are the things we'll need there. Okay? We'll need to calculate a couple of things. One of the things we'll have to calculate is acceleration. But we're using a different formula than the one we've used in class. This is the only time you'll need this formula. Okay? I'm never going to ask you to use it again on a quiz or a test. Okay? But the acceleration will be 2 times the distance divided by time squared. Okay? That's why we have to record the distance it travels after and the time it travels for. Okay? That'll help us to get the acceleration of the cart. Okay? We will calculate the force of friction, okay, by going mass times acceleration, or actually, we'll do this. We'll calculate the kinetic energy of the cart by going mass times acceleration times distance, which is really this calculation right here. The force of friction times distance. So we'll have the mass of the cart, we'll have the acceleration of the cart, and we'll have the distance it travels, and that'll get us our kinetic energy at the bottom of the ramp. Okay? Everybody with me there? Okay. So those are the things that we'll have to calculate, okay? And then we'll have our, oh yeah, so this is me explaining it all. So force is mass times acceleration. Not a formula you're going to need to use, okay, other than today. Okay, so when we calculate the acceleration, these are our measured values, d and t. Okay, we calculate the acceleration, we plug it into this formula. Since force is mass times acceleration, force times distance is work. Mass times acceleration times distance is work. Everybody okay with that? Okay, we're just substituting. In the end, as long as you do that, you're good. Okay, that'll get us what we need. Okay, so this is like some sample data here, okay? It's from another time. These were the numbers that I got. Traveled for about 10 seconds each time, traveled about 4 meters each time. Okay, that's kind of what happened for me. And you're going to do 4 trials, same height. Okay, we're not trying to compare different amounts of potential energy. We're just getting 4 trials so that we can average it out, because there is some inconsistency with the carts. Okay, you can see there that me being extraordinarily careful, I still had a bit of variance, okay, in the distance traveled and a bit of variance in the time of travel. I had one here that was almost a half a second faster than the others. Okay, that's why we're doing 4 trials and averaging the trials out. Okay, for our analysis, calculate the work done putting the cart at the top of the ramp. That's just this. Okay, you're calculating the potential energy at the top of the ramp using the numbers you have. Okay, you're calculating the acceleration of your cart for analysis question number 2. So that was the 2d over t. Show your work. Okay, calculate the kinetic energy. That's mass times acceleration times distance. Okay, and this one here is 2d over t squared, okay, for number 2. Okay, number 4, I've actually explained this already. Outlined how you determined the potential and kinetic energies of the system. Be detailed. Okay, this is what you need to know for question number 4. I'm not looking for you to tell me how you calculated it. I already saw that. Okay, you've already shown me your calculations. I need you to explain to me why you did those calculations. Okay? If you recall, I was talking about earlier what force is stopping the cart. How are we using that part of the motion to determine what the kinetic energy at the bottom was? How did we determine how to get the energy at the top? Okay? What did we do there? Talk about the types of energy. Talk about work. Okay? Talk about force and distance and all of that. That's what I'm looking for in question number 4. Okay? Don't quote me your math. I can already see your math. I'm looking for it. You telling me in words, okay, what happened? Okay, how did you get the energies? Okay, and then for number 5, very simply, did the potential energy of the system equal the system's kinetic energy? Spoiler alert, the answer is no. But you have to explain why. Okay? Talk about where some of the energy went. And now, for this part, we're only talking about on the ramp, between the top and the bottom. We do a whole bunch of calculating for stuff that happens after the bottom of the ramp, but we're only worried about the energy conversion between the top and the bottom. Okay, is the energy at the top and the energy at the bottom equal? Why or why not? What happens along the ramp? So it might not be a bad idea to make a few qualitative observations about what you notice as the cart goes down the ramp. Okay, after the ramp, no big deal. We don't need to worry about that. We're using it to calculate some stuff, but that's not what we're comparing. Okay, does everyone follow me on that? Okay, and there's an observations video of me doing this lab as well, okay, in case you missed something and you just want to go over it again, okay, you can kind of see what the cart and hear what the cart sounded like and all that kind of stuff as it went down the ramp. Okay? All right, questions from you guys? Okay, so here's how we're going to do this. I don't think there's anybody in the chem lab. Okay, so I'm going to put some of you in the chem lab, and I'm going to have some of you in here. Okay, you need to have a fair amount of space in order to do this lab. Okay, so I'd say like maybe one group can go here at the front. It's actually the front of the room where I did the experiment. And that was plenty of room. I started about right here, okay, and my cart ended about right here. That was plenty of room. So we can have one group at the front, one group at the back. Maybe another group can go kind of down one of these aisles, okay, and there should be room for that. And then in the lab, pick some of the diagonal spaces that go between the lab stations, and that should be lots of room. Remember, 15 centimeters tops is as high as you need that ramp to go. You go any higher than that, I guarantee the cart will hit the wall. Okay, it will go too far. Okay. All right. Any questions before you come up and grab the materials you need? Okay, remember, black carts, wooden ramps, silver carts, silver ramps. Okay? All right. Okay, so remember that for the analysis, the bulk of it is just performing the calculations that we talked about. Calculating the work done to put it at the top of the ramp, m times g times h. Okay, to calculate the acceleration of the cart using average distance and time, 2 times d. Divide that by t squared. Okay, and then to get the kinetic energy of the cart, mass times acceleration times distance. Okay, so those are just, and show me your work. Okay, either you did it on paper and you're putting in a picture, or you're just typing it in, whichever. Okay, and then for number 4, outline how you determined the potential and kinetic energies of the system. Again, that's an explanation. Don't show me your math. Don't talk about the math. Talk about the experiment and what happened qualitatively. Okay, in that explanation, okay, and then potential energy, does it equal the system's kinetic? Suggest reasons for why or why not. For your conclusion, copy paste your hypothesis, okay, and explain why or why not you can accept or reject it, okay, and then for your evaluation, sources of error, okay, think about what happened to the cart as it went along, okay, things like that, anything that might have been an inconsistency or something that could be fixed, right, same as always.